and I'm working on a combination of M theory, string theory, doing numerical simulations on a computer. And my research is slightly connected to the topic of extra dimensions. And this is a very popular topic, so I'll give you a short introduction. And it will be connected since this lecture is presented online with www. The first W is what are extra dimensions? The second W will be why we think they might exist. And the third W is where can you find them if they indeed exist? So let me start with the first question. What are dimensions? Let me start with the basic 3 dimensions and we will add the extra later on. So basically, dimension is a property of space that captures in how many distinct directions we can move. So let's go over some examples and it will be very simple. For example, a rope is a one-dimensional space. That means that if you're sitting on a rope, you can only move up and move down. So we would call a rope a one-dimensional space. Then a simple example of a two-dimensional space can be, for example, a sheet of paper. You can move up and down, and you can move left and right. So a simple example of a two-dimensional space. And for a three-dimensional space, we can take, for example, our Earth. You can move up or down, left or right, or back and forth. Or in the case of a globe, we usually say we are moving north and south, east and west, and then up and down. So 3 distinct directions that we can move. So let me repeat, we call a rope a one-dimensional space, a paper a two-dimensional space, and our world is a 3-dimensional space. Now let's gear it up a bit. It's hard to give a name to something 4-dimensional. Usually we call it like a hypersphere, a hypercube, but we don't really have good names for this. But we can actually say what does it mean to be 4-dimensional? It means that you can move in 4 distinct directions. So it will be up and down, left and right, back and forth. And again, we like the vocabulary to describe the new direction. So it can be like hulu and malu, like back and forth in the 4th dimension. And actually there is one more example to go over, and this is a 0-dimensional space. We usually call this, for example, if you have only a single point, so we call a point a 0-dimensional space because you cannot move if you are stuck in a point. Now, well, you probably didn't come to see 3-dimensional space, you want to see something more. So let us discuss the extra dimensions. This was just the base ground. And well, to imagine an extra dimension is something borderline between very difficult and impossible, because, well, our brains are not just developed to do this. If you grew up in 4-dimensional space, it would be natural, but otherwise it's very difficult. But, well, the good news is actually that we don't have to do it. We don't have to imagine how the world looks in the 4th or 5th or 6th dimension. For example, let me explain why we as physicists don't need to actually imagine living or moving or doing anything in the extra dimensions. So imagine I have a fly in my room. So I want to call a police and say, hey, there is a fly in my room. They will ask me, where exactly is this fly in your room? So I have to give some kind of coordinates. So I have to set up a coordinate system. And since our world is 3-dimensional, I have to specify 3 numbers to describe where the fly is in my room. So I would have to provide 3 different numbers describing the X, Y, and Z coordinate of the fly. Now, well, for me to describe the position of a fly in my room means to give 3 different numbers. So in this case, 0.6, 1.4, and 1.6. Very simple. Now it's easy to see how could we generalize this into, I don't know, 4-dimensional case. In 4 dimensions, to describe a position of something, you need to give 4 numbers. In 5-dimensional space, to give a position of something, you need to give 5 numbers. And now as the fly is flying in my room, those 3 numbers are changing. So movement in 5 dimensions is described by 5 changing numbers. So it's actually fairly simple. And this is something that we are doing a lot as physicists, because, for example, imagine a terrible scenario. There are 2 flies in my room. Now, to describe position of 2 different flies, I need to give 3 numbers for the first fly and 3 numbers for the second fly. So altogether 6 numbers. But from a different point of view, a position of 2 flies in 3-dimensional space is equivalent to 1 point in 6-dimensional space. It's just a set of 6 changing numbers. So for a physicist, this is very natural because, well, we often describe a system with many degrees of freedom. So we are used to work with a lot of changing numbers. So adding dimensions seems fairly natural to us. But well, okay, this was a little bit of cheating, but this is what the physicists do. We use math to describe nature, and using math, it's fairly simple to describe extra dimensions. It's just a bunch of extra numbers. But okay, it's hard to appreciate the differences between 4-dimensional space and 3-dimensional space only using numbers. So to sharpen our imagination, we can try this exercise. We will step down a bit. We live in a 3-dimensional space, and we can step down to 2-dimensional space. So imagine how it would feel to live, for example, on a sheet of paper. You can move only in 2 directions, up, down, left, right. And you cannot move back and forth. This is forbidden in this example. So there are many tricky situations. For example, if you are a living cell, then you probably need to digest food. So you have some sort of mouth. Then there is the digestive tract going through your body, and then the place where the food leaves after you are done with it. And if there is a line connecting through your body, it actually splits your body into 2 different parts. So in 2-dimensional space, any biology would have to be very, very simple, probably too simple to actually be a biology, because if you connect something with a line, it splits the thing into 2 parts. Then another issue is that, for example, in a 2-dimensional space, you cannot tie a knot. You cannot tie a rope to form a knot because it would intersect itself. So it's something that we can do in 3-dimensional. We can easily tie a knot, but well, in 2 dimensions, it's impossible without some sort of intersections. And another example is, for example, if I want to catch a fly in 2 dimensions, I just need to put a circle around the fly. And if I put a circle around the fly, it cannot escape. It would have to go through the line to escape, which is impossible. And in 2 dimensions, it cannot fly in the 3rd direction, in this case up. Okay, so we got used to 2-dimensional space. Now return to 3 dimensions. In 3 dimensions, if you have line connecting 2 points, it doesn't split the world into 2 parts. To split something into 2 parts, you need to cut it with a plane. You can tie a knot. For example, the one in the previous example is called a trifle knot. And you can do it without intersections. And actually, to catch a fly, you need to surround it with a sphere. So sphere is a 2-dimensional space surrounding a fly. And now the fly cannot escape. And now the fly cannot escape without crossing the sphere. Okay. And now, well, we can again go 1 dimension up and see what are the differences. What difference does it make now? Well, for example, now a plane doesn't split an object into 2 parts. A plane is like a line in our. So to cut something into parts, you need to use a 3-dimensional object such as volume. Another thing, a fun thing about 4 dimension is that any knot you have can be untied in 4-dimensional space. There is actually a mathematical proof that you can do this. So if you tie a knot, then you can go to a 4-dimensional space and just push it apart and it will open itself. And actually during, I think it was mid-18th century, it was a common party trick. People claimed that they are able to visit 4-dimensional spaces, and they proved it by untying knots. So it was just a simple magic trick, but they claimed they do it by visiting a 4-dimensional space. And in 4-dimensional space, to catch a fly, you need to surround it with something called a hypersphere, which is a 3-dimensional sphere living in a 4-dimensional space. So there are actually a lot of differences from adding one more dimension. But still, it isn't, well, imagining the extra dimension. And there are two tricks for imagining 4-dimensional objects that I know of. One of them, for me, is very bad and doesn't really work, or it's very misleading. And the other idea is actually very good, at least it works for cases. And the bad idea is to imagine 4-dimensional space using shadows. In our space, we are 3-dimensional beings, and we are casting 2-dimensional shadows. So people often say that, well, 4-dimensional beings are casting 3-dimensional shadows, which makes simple. But, well, shadows can be very misleading. Just consider this example, a shadow of a cat that looks like a howling dog. So for me, shadows aren't really working. But I like the other example, which is tomography. Tomos is a Greek word which stands for slice. And tomography is an idea that we can actually describe 3-dimensional objects, in this case, a human skull, using a set of 2-dimensional slices, 2-dimensional pictures. So this is the scan going through someone's head, probably from the top to the bottom, I think. And by adding a lot of 2-dimensional pictures, we can get an idea about the real shape of a 3-dimensional space. So this is the idea with tomography. The tomography, by adding a lot of pictures of one less dimension, we get an idea of how the space looks like. So we can do this with 4 dimensions. Slices of 4-dimensional space are 3-dimensional, so objects in our 3-dimensional world. So the simplest examples would be slices of a hypersphere, of a sphere in 4 dimensions. The first slice, as we said, slicing 4-dimensional space required volumes. So the first slice of the hypersphere is a very small sphere. The next slice is a slightly bigger sphere. Next slice, bigger sphere. And then as we are moving forward with our tomography, the sphere is again shrinking. So in this picture, you can see a series of slices of a 4-dimensional sphere, which just turns to be a series of 3-dimensional spheres of an increasing volume. So for me, this is the only working way of imagining the 4th dimension. And it's difficult to increase the dimension to go to a 5-dimensional space. But it works for 4-dimensional space. So be happy about it. Now, actually, we avoided a good example of a 4-dimensional space, because actually Einstein showed that our 3-dimensional space can be very naturally joined with time to form something we call space-time, which actually is a 4-dimensional space. And in this four-dimensional space-time, we can move up and down, left and right, back and forth. And actually the 4th dimension in this case is the past and the future. So this is a very, very nice way of imagining 4-dimensional space as a sequence of 3-dimensional spaces. In this case, sequence means a temporal sequence, like different slices are different times. There is a minor difficulty with the space-time that the time and the space is being treated on different footnotes. So it's slightly different, but it's a very, very intuitive way of thinking about 4-dimensional spaces. Now, this was the first W. What are the extra dimensions? Now, why do we think they might exist? And I will begin with a slightly bad slide, because this slide shows that basically physics in any other case as 3 dimensions plus 1 time is meaningless. For example, if the number of dimensions is 1 or 2, that is just too simple to form life as we know it. On the other hand, if you, for example, have more temporal dimensions, like having 2 or 3 times, the physics just wouldn't work as we know it. And then there is one sector when you have 1 time, as we do, but more spatial dimensions. So for example, 1 time plus 4 dimensions. And you can see that it's marked as unstable. And this is because of the fact that the world, as we know it, works because of a very fine balance between different forces. For example, the stability of atoms is because of a balance between centripetal force or centrifugal force and a Coulomb attraction. And now these forces work differently in higher dimensional spaces. And the sweet balance, the sweet spot between when the forces are balanced, is completely ruined in higher dimensional spaces. So if you actually move to a 4-dimensional space, as the party people claimed in the 18th century, then the all atoms in your body would collapse or explode, one of those. So actually matter as we know it isn't stable in more dimensional spaces. So perhaps I could close my talk with this slide, because it just proves that anything else that 1 time plus 3 dimensions is meaningless. But actually there is a loophole, and we'll get there fairly shortly. But just let me give you a short history of theoretical physics of the last century, of the previous one. And 2 most important figures, for me at least, are Maxwell, which is basically end of the 19th century, and then Einstein, beginning of the next one. So Einstein and Maxwell, and both of them discovered amazing theories. They pushed forward our understanding of the nature as no one else did. Einstein discovered the theory of relativity, which describes the force of gravity as being just a manifestation of a curved space-time. And it's described using an object which is called a metric tensor, which is called G in this picture. Then Maxwell described electromagnetic fields using mathematical fields. And then we discovered that actually they can be described using something called vector potential. And this is like their legacy. Case is a matrix, which is a table of 4 times 4 numbers. In Maxwell's space, he had a vector which had 4 numbers. So Einstein had 4 times 4 object, and Maxwell had just object of size 4. And now 2 new names. One of them is Kaluza or Kaluza. It's very difficult to pronounce his name because I think he was German, but born in a Polish city. So either Kaluza or Kaluza works. And the other guy is called Klein. And well, they realized that those 2 objects, the metric tensor from the Einstein theory of relativity, fits perfectly with Maxwell's vector potential that describe electromagnetic fields. And they are fitting together perfectly. And they try to understand how to interpret this new mathematical object that they got. And the new mathematical object actually is 5-dimensional. So it's something that seems to be living in a universe that has 4 spatial dimensions as a 3 plus 1 plus 1 time. So it was very weird because obviously we are living in a 3-dimensional space. What's up with the 4th dimension that they saw as a natural explanation for this merger. So they formed this new object, and they thought about, well, what is the origin of this one? They knew that in this four-dimensional universe, 4 plus time dimensional universe, the gravity and electromagnetism perfectly fit together. And they found an interesting interpretation for this one. And let me stop sharing my screen for a while, because I just want to show you an example. So they think of the 4 dimension as being a small circle. What does this mean? This means is it, and I can roll up the paper. So actually, when I roll up this paper, it actually looks like a rope, a one-dimensional space. If I roll it up very tightly, it will actually resemble a small, tiny rope. If it's not so tight, then it actually looks like, I don't know, a cylinder or something. So they were thinking like, well, what if we are not seeing the 4 dimension because it's just very tightly curled up? It's minuscule, it's very small, and it's nearly impossible to get into it. And actually, they also found out that depending on the size of the extra dimensions, the charge of the electric current depends on the size of these extra dimensions. It is coupled to the electromagnetism in a non-trivial way. And it actually means that the size and the structure of the extra dimension influences the laws of nature in the 3 plus 1 dimensions that we are seeing. So let me repeat this point. The shape and the size of the extra dimensions influence the laws of nature in the 3 dimensions that we can perceive. Now, just a minor point that, well, I told you that I'm working a little bit on a string theory and M theory. And in this case, for the superstring theory to be consistent with mathematics, it requires the space to actually be 10-dimensional, which means one space plus 9 spatial, one time plus 9 spatial dimensions, 3 of which are large and 6 of which are very small, but the shape of the small compactified dimensions can influence the laws of nature as we perceive them. So from the point of view of string theory, in every point of our space-time, there is a tiny 6-dimensional world curled up and influencing nature as we see, as we perceive them. And now, where can we find the extra dimensions? Now, as usual, there are good news and there are bad news. The good news is if the extra dimensions indeed exist, they are everywhere. It means that in every point of our space, we can actually move in another direction, in a 4th direction, and possibly in a 5th and 6th direction. The bad news is that they are tiny. And by tiny, I mean very, very tiny. And the ballpark estimate is their size is between 0.20 up to 35 zeros, 0.1, not point, just 1. So they're very, 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 very small. Hard to get inside them. So how to become small in physics? When Alice wanted to wander in the wonderland, she needed to become very small. So she found some kind of a potion, which she drank, and she became very small. Well, getting small in physics is way more expensive. And let me explain on the case of electromagnetic waves. In this case, the energy of the radiation is inversely proportional to the wavelength. So the shorter the wavelength is, the larger energy it has. So for example, we have visible light, which is, I don't know, 4 to 800 nanometers. Then we have radiation of longer wavelengths and smaller energies, such as radio waves. And on the other hand, we have waves that are smaller, but have higher energy, such as X-rays or gamma rays or ultraviolet light. So becoming small means adding a lot of energy, concentrating it into a very small pile. So small dimensions requires small wavelengths. Small wavelengths require high energies, and high energies require, for example, large particle colliders. For example, LHC in CERN is the largest particle collider. It's a large hadron collider, and L stands for large. It's very big. And well, if the extra dimensions are as small as we believe they are, they should be on the so-called Planck scale, then the hadron collider energy output would need to be increased by at least what is the number? It's million of a billion times. So by 15 digits increase, which would require probably a particle collider of the size of our solar system, which is impossible to make. And this is something that you can actually call like the tyranny of small dimensions, that getting or testing or doing anything with extra dimensions require very high energies, which may mean it's nearly impossible. And there are some workarounds. For example, it was, I think, 10 or 15 years ago, they were thinking in CERN that, well, maybe if the extra dimensions really exist, there is a lot of them, then maybe the gravity is escaping into those new dimensions, into those extra small dimensions. Then it's like leaking, so more or less. And in this case, the behavior of black holes would be different as we know them now. So in case there are many extra dimensions and the gravity can leak into them, then we can probably make a very small black holes in CERN. They would quickly evaporate because of Hawking radiation, but they would leave some kind of evidence, some small gaps in particle rays or something like that. So we would be able to detect those small black holes that exist because of extra dimensions. This didn't turn out to be the case, and they actually put this leg of evidence, put some restrictions on the number and size of the extra dimensions. So this gave the estimate that the size of the extra dimension has at least 20 zeros in it. So this number is coming actually from experiments, this restriction. So there is one way of hoping to detect extra dimensions is to create a clever experiment that would allow you to detect it. The other thing is that actually, maybe we might just get lucky, because there is something called cosmic rays. Cosmic rays are mostly high energy protons coming from distant supernovas and active galactic nuclei. And their energy sometimes can be between the energy we can produce in CERN and between the energy needed to enter extra dimensions. So it isn't completely out of the question that if the nature can actually produce particles that can enter the extra dimensions, it's still a lot of magnitudes below the threshold, but it's not completely impossible. So I, as a theoretical physicist, will be looking forward to this direction of research of ultra high energy particles. There is, for example, something called oh my god particle that actually broke something called a speed limit for protons in our universe. And there is a non-zero chance that they will allow us to learn something about the extra dimensions. They can serve as probes if we are clever enough to design a good experiment. So the final question, are there extra dimensions? Well, definitely maybe. There are good signs, there are good hints, but we lack the evidence. We lack the evidence because, well, it's just out of our reach. But well, whether we are able or not to test it, they can exist, or maybe not. So people are looking into this issue, and we are not expecting that we will be able to detect them anytime soon. It may take decades, maybe, but it's still worth investigating, because if they indeed exist, it can have a profound impact on our understanding of our universe. Because if the extra dimensions indeed exist, they are probably the reason our laws of nature, the laws of nature that we know of, work as we know they do. So very hot, very interesting topic. And this is probably everything I had. So thank you for your attention.
Anybody who has any questions, you can post them in the chat box there at the bottom. But I just had one question for Samuel, first and foremost. Do you believe, I suppose, in the work that you do already, but do you believe that extra dimensions exist, and what within your own work are you pursuing to try and prove it, if so?
So, well, as a scientist, for me, it shouldn't be about a belief, if I do believe or not. It's about gathering evidence. And at the moment, we have gathered theoretical evidence. It's more than plausible that extra dimensions indeed exist. And now we are thinking of a way to actually prove them. So I wouldn't say I believe them. I believe that they exist, but I can appreciate the indirect hints enough to spend some time investigating them. And actually here at DICE, we are working on matrix models coming from M-theory, which are actually describing how the 3 dimensions can grow. And they could explain the discrepancy why 6 of them are very small, compactified or curled up, and 3 of them somehow blew up. And the process of 3 dimensions blowing up is probably the phenomenon that we call the Big Bang right now. So it was the moment when the 3 dimensions started growing.
Okay, great. We do have a couple of questions now. So the first question is from Martin, and he was wondering, how are these dimensions compatible with the extra dimensions in the membrane universe? He's saying the extra dim looks bigger.
Well, there are different types of membrane universes. Basically, the idea is that string theory says that we should have 9 dimensions, and we only see 3. So the idea that maybe we are stuck to a 3-dimensional membrane, and that's why we don't see the 6 other dimensions. Now, there are different aspects of the membrane universes, and it's hard to say what we are comparing here. In most cases, all of the 6 dimensions should be very small, way smaller compared to anything else. So, for example, like distance between 2 closed membranes and things like that. But there is a model of the universe, I forgot the name right now, which has branes, which has distances comparable to the size of the extra dimension. So we don't know at the moment. It's hard to say when we like experiments.
Great, thanks. The second question that we have here now is from Simon Purser from DICE. And what would slicing a 4D object along with either X, Y, or Z look like as opposed to the 4th dimension?
So in my example, we are slicing 4-dimensional sphere. And I chose sphere because sphere is spherical. It doesn't depend along which direction are you slicing it. It looks the same from any direction. For example, slicing a 4-dimensional cube would be more complicated. And I don't know how it would look like. I would need to use some kind of computer language as mathematical to give me the answer for this one. But that's why I chose sphere, because it doesn't matter along which dimensions where we're slicing.
Okay. Our next question is from Aaron, and he is wondering, when looking at these high energy cosmic rays, what would be the telltale signs that they pass through an extra dimension?
So the possible sign would be that we don't see any cosmic ray above a certain threshold. It has the energy. If it has the energy to leave into the extra dimension, it would. and you wouldn't see it here. So if this is indeed the case, there should be a very sharp energy level that we can see some cosmic rays of energy below this threshold and nothing above it. So something along these lines.
Okay. Our next question then is from Jeff, and he says, thank you very much for your talk today. He's wondering, so we could have dimensions with different properties like size and directionality. Is superstring theory predicting other potential properties?
So we physicists usually just call dimension something that you can move in. So we are not saying only different dimension, like in this case, what was it? Size, direction. Okay, this is something that we would call dimension, but it is a dimension as something you can move in, but it can be dimension of a different, for example, topology. It doesn't have to be a straight line. It can be a circle. It can be a donut shape. It can be a shape of something with a weird name like a Calabi-Yau, so something weird curl up, as was shown in my picture. The moving things were so-called Calabi-Yau manifolds. So picture anything you like.
Okay, thanks. The next question is from Linda and Dinny, and they are wondering, how would a holographic understanding of the universe fit with extra dimensions, and can several dimensions exist in the same space?
So for those who doesn't know what is a holographic description of our universe, it's somebody noticed that actually anything you put inside a sphere can be described by what's happening on the sphere. Like the information you can squeeze into a sphere can be encoded into the surface of the sphere.
Okay.
So three-dimensional sphere is described by two-dimensional boundary. And somebody is saying that, well, our universe is three-dimensional. Can it be described as using a boundary of our universe if it has one? And if our universe is indeed 10-dimensional, well, maybe it can be described as using only the surface of the universe. But actually, the holographic principle is much more useful in the string theory, because in the string theory is connecting two different aspects of physics. It's connecting theories of interacting particles with the theory of gravity. And this is something we are also working on here at DIAS. We are testing something called holographic principle. We are using theory of gravity to make predictions, and then we are making numerical computer simulations of interacting particles to test them versus the gravitational predictions. So actually the holographic principle can play much deeper, much more important role that we can imagine at the moment. And we are testing the possibilities right now.
Great. Okay, so one new one has just popped in there just as I was about to close up. This one is from Martin again. He is wondering, is there an easy way to understand an easy to understand way why the string theory needs more than 3+1 fifths?
No. I'm sorry, but it involves complicated mathematics, quantization of Virasoro algebras and things like that. So it's impossible to give just a wave-handing argument for this one. So sorry about this. It's just a result of many different computations and calculations.
No problem. Some things aren't meant to be too easy, Samuel. You know?
Yeah.
Okay, well, if anybody has any more questions, feel free to type them into the chat there. I am just going to tell you a bit more about a couple of more of our sessions that are coming up. So these sessions are going to run continuously now until June 11th. And then on the week beginning the 15th of June, we're going to have some very kind of DIAS focused events because that actually leads in to our DIAS Day events or the week, I suppose, that the Act was officially signed that brought DIAS into being. But between now and then, we have 2 more lectures, and we have another event as well, which is to kind of commemorate some of the science that is kind of a part of Bloomsday and Bloomsday celebrations, which obviously have all been moved online. So the next lockdown lecture will be held next Monday, the 8th of June, and it is called The Thoughts of Schrödinger and Hamilton That Stood the Test of Time, and it is being delivered by our DIAS student called Luke Koopman. And then following that on Tuesday, the 9th of June, we will present the Joycean Evening, and that is entitled The Heaven Tree of Stars. And that'll begin about 6:37 p.m. But full details again are on our Eventbrite there. So if you'd like to attend that, you can reserve a place. And then the last of our lockdown lecture series will actually take place on Thursday, the 11th of June. And it's being delivered, should I say, by a previous staff member, but he's not gone that long. He only left just in December. Dr. Leron Borston is going to present his lecture, which is titled, I think it's the Road from Dunsink to 11 Dimensions. So he's saying there's a few more dimensions there than you were today, Samuel. So that'll be an interesting kind of follow on from today's talk. Let me see if anything else has come in since I have been rabbiting on.
I answered the questions in the chat.
Is there a new question? Oh, yes, another one there from Aaron. Did I go too far back, or is there more? Oh, there is more. Oh, God, everyone's been busy while I've been talking. Okay, so the first question that has come in, while I was advising you about our upcoming events is from, oh God, forgive me for butchering this, Bala Vignesh. And is there any possibility for unified theory?
Yes, I answered in the chat that string theory, or the string theory, is the prominent candidate for a unified theory of all forces of nature. It contains particle theory both as a gravity, but it's far from being perfect. Extra dimensions might be one of the issues we need to resolve before claiming to know the perfect unified theory.
Okay. And then following on from that, Aaron has another question. He says that you said that physics would be impossible in other combinations of dimension, space, and time. Can there be some laws that would allow some form of physics to be viable in higher dimensional worlds where the dimensions are not compactified?
So I said that it's, well, close to impossible having extra dimensions that are not more than 3 and less than 3 extra dimensions. But actually there was a scientific paper last year about a possibility of having complex life in 2-dimensional world. So it's maybe not impossible. It was coming from something called graph theory in math. But laws of nature allowing something we would call life, or something interesting in 4-dimensional space, well, I don't want to say it's impossible. I haven't given it enough thought to say so, but at least it's very hard to imagine something working there.
Okay. So we've had 2 more questions since as well. Jeff is wondering, would quantum computing help in any way with detecting extra dimensions?
I don't think so. It's still very, very far away. And they would help us to tackle different issues, not extra dimensions. We just need to build larger colliders or have to be lucky with the cosmic rays.